Welcome to this prestigious Geological Society location. And I'm looking forward to hearing lots of information. And the objective today was actually suggested by the previous president of the Geological Society, Edmund Nicholas, that we would be able to hold a regular series of forums. So I took him up on his offer. And it's more information exchange, some discussion, and, if you like, conversations about what research can do for our understanding of the deep subsurface in relation to shale gas. And this is the second. There's been one before. This is the second. It's funded by Horizon 2020 research program from Europe. And the end product of the research between the group that is running this one, Shale X Environment, which Alberto is leading, is going to talk about. The end objectives are to produce guidance and recommendations for best practice and even information which will go towards governance of the potential shale gas industry in Europe and the UK, for example. And Chris McDermott is here too from Edinburgh, who also represents one of the other 3 simultaneously funded shale research programs, which started 2 years ago and have 1 year left to run, approximately. So he's going to talk a little bit this afternoon too. And so with that, I'd like to just thank, first of all, Evgenia and Natalie for helping in the organisation, and which is very helpful to me. And they're from the European office at UCL, and European office at UCL is very helpful in all of our research efforts for this sort of program. I don't want to take up too much time, so I'm going to keep this very short. And hope you have a very enjoyable day listening to people talk from their different points of view. And store up your questions during the day is probably the best route. And then we'll have a period at lunchtime when we can see the posters, and also interact and talk, ask questions. But there will be a panel discussion this afternoon as well, where you may like to ask some questions. So we'll have some guidance on that too later on, but I look forward to the rest of the day. Thank you. Alberto, please take the floor.
Well, good morning, everybody. Thank you for coming. My name is Alberto Striolo. I'm a professor in the Chemical Engineering Department at University College London. And I will start by thanking Adrian for putting the forum together. Adrian is from the Earth Sciences Department at University College London. And anything good today has happened because of his efforts to put it together with Eugenia and Natalie that have provided extremely good support. Thanks a lot. All right. So Adrian and I lead this consortium, Shale X Environment. And it's one of the 4 consortia that have been supported by the European Commission to try to study shale gas and to try to give some suggestions on how it is possible, or it might be possible, to reduce the environmental impact of such technology. What I will try to do in the next few minutes is to give you an overview of what the consortium looks like and what we are trying to do in the various parts. And I will try to highlight the people that have done the work, really, and some of the work will be discussed in details during the presentations later on. So let me get started. So in this slide, I summarize, first of all, the members of the consortium. You see all the names out there. We are actually expanding a little bit this consortium. We have a collaboration with Imperial College that has been very fruitful. Ronnie Pini is sitting here. Thank you very much. And we are expanding with a new partner, the University of Huelva in Spain, that will provide some unique capabilities for the consortium. What we thought 3 years ago now was that perhaps shale gas could provide some new opportunity in Europe, perhaps in providing new sources of natural gas for the continent, really. But we recognize that we need to know a lot more about shale gas if we want to make it, if you want to produce it in a way that respects the environment. There are challenges. Some of these challenges are technological, some are scientific, and a lot of these challenges are in communication with the public. So we recognize the need of keeping an open communication with the community, and this forum is really one of the many efforts that we have put in place to keep this communication going. This is the way we have proposed to actually tackle the research. So the final goal is to try to have an idea about what is the environmental impact of shale gas. How do we go about to get that quantity? What is the environmental impact? So our idea was that we need to get information about every single formation. So we need to have access to the rock samples. We need to study the rock samples. We need to understand how the fluids behave in the rock samples. Once we understand that, we might be able to predict how much gas can be produced from a formation. At that point, we should estimate the impacts on the environment in terms of water consumption, emissions, if there is any. And then we can put those two terms one against the other. And this worthiness factor, this W that I put up there, is a way that we have proposed to quantify essentially the risk versus benefit of working in the shale arena. Okay? Now, deciding when that worthiness factor is sufficient to proceed in an operation or not, that is a decision that we cannot take. That is a decision that is up to all the stakeholders that are involved in the operation, going from politicians to people living near the well bores. So there we cannot influence other than sharing what is that we found scientifically. So what I do now, I go through the various steps, and I show you what is that we have been trying to do for the past 2 years, and what we are trying to do for the last remaining year. So the first step was to have access to shale samples. So we have been lucky to have access to cores from the Boland Formation in the UK. A lot of our work has been done on those core samples. This is a graph that shows you the well depth at which the cores are available in a specific location. And the red dots are some of the samples that we have retrieved. And we are doing a lot of experiments using the same samples so that we have a good understanding of what happens in those specific rocks. The list there provides some information about additional rock samples that we have access to. And some of these have been provided by our commercial partners. Thank you very much. We cannot disclose where those rocks come from for commercial reasons, but we can do a lot of the science to try to understand what happens inside of those rocks. This is an example of characterization. This is work done at the University of Manchester. We will see much more after my presentation. This graph over there, it's basically 3.25 millimeters of rock. And what you can see there is that the rock composition changes quite significantly within those 3.5 millimeters. Organic content, quartz content, any type of the rocks that is present in there changes quite significantly in there. Now it's quite understood that shale rocks are very diverse, and we cannot just use average properties for them. When we started this work, that was not widely accepted. So that is a little bit of a contribution that we have made to the community. I should say that Manchester, for the most part, has done to the community. This is some work that comes from UCL. Niels will talk about this later, but Francesco has contributed quite significantly to obtain these results. These are tomographic measurements that look at a very small piece of rock. You can see a little bit here. This is how big that sample is, 60 microns. So very, very small. But this technique allows us to actually see what we think are the pores inside of this rock. And what our colleagues were able to do, and this is Tom Mitchell and Adrian's colleagues in the Earth Sciences department, was to measure the permeability in the direction perpendicular to the pores or parallel to the pores. So now we have quantitative measurements of the transport properties of the fluids inside of the rocks, and we can relate them to the visual inspection of how these rocks look like and what is the chemical composition of these rocks. We combine this characterization experiment with mechanical property testing. This is work done at Potsdam in Germany. So essentially, we pull these rocks until they break, and we measure stress-strain curves. And what you see here, let's see if I can show you, these three curves over there are samples from the Marcellus Formation in the US, as well as from the Boland Formation in the UK. So what that tells you is that if you make a little bit of a strain, you are actually breaking those rocks. You need to pull them with a significant strength, but they do end up cracking. Whereas other shale formation down here, they can show a very large deformation before they crack. And on this part of the slide, we are showing some results that Potsdam obtained, and that are similar experiments, but now as a function of temperature. So we want to understand how the conditions in situ affect the properties of the mechanical properties of the rock. This is important because if you want to produce shale gas, you will have to frack the rock. And these type of experiments tell you how much water you need to inject if you want to crack those rocks. This is another slide that comes from Manchester. Manchester is a significant contributor to this consortium. And we will learn more about this. This is work done in collaboration with Diamond. What I particularly like is this part of the slide, where basically a small piece of rock is put under an instrument, and a fracture is initiated inside of the instrument. So our colleagues are able to see how the fracture initiates and how it propagates inside of the rock. This is quite exciting results because it actually tackles one of the grand challenges for our understanding of the subsurface. So I'm quite excited about these results. So now I change scope a little bit. I show you a little bit about what the experimental parts are in our consortium. Now the next thing that we want to do is to try to understand and predict the properties of the fluids. So what we are doing there, we are tackling a large range of length scales. So we go from very small length scales, in which we want to understand how the fluid behaves inside of a very small pore. And then we want to see how we can understand the transport of fluids when many of these pores are connected to each other. And then we want to go all the way to try to predict how the fluid come out from the formation and how much of the gas can be produced. That's also quite a challenge. We are not there yet, but I'll show you a bit of the things that we have been doing. So this is the type of work that my group does, but we have many partners in the consortium that are involved in this. Kalinichev is from France, Lizali from the Czech Republic, Economou is from Greece, Cole is my old friend, he works at Ohio State University, and we have a number of people working in here. So this is modeling work. So we look at experimental information. We represent those pores in a simplified way, but we are able to describe every single atom in there. And then we try to predict, for example, the solubility of methane in water when that water is confined. And what we found was that actually the solubility of methane in water can be 1 order of magnitude when the water is confined compared to bulk water. On the opposite side, if we look at the solubility of salt, what we found is that the solubility of salt goes down when water is confined in a small pore. So we have two different behaviors in there, and we are trying to understand why they are so different. In one case, the solubility goes up, and in the other case, the solubility goes down. What are the implications of those results to our impact to the environment or the technology? We still don't know, but we are working on that. Then we go back and try to validate our results. So our colleagues in the Czech Republic, they are producing zeolites. These are some images of these zeolites. We use them to measure the adsorption isotherms in these zeolites, and we can compare those to the simulations. So these are a couple of comparisons in which we have essentially quantitative agreement between experimental and simulated adsorption. So we believe that we understand the behavior of the fluids. And we gave some samples to Ronnie, who's measuring similar experiments for the shale rocks that we have characterized earlier. The next step from these modeling studies will be to go from one pore to permeabilities in larger pores. Traditional approaches are based on effective medium theories, for example. And unfortunately, we know that they don't work. So what we are doing, and this is in collaboration with Ali Barton, is coming up with a kinetic Monte Carlo approach in which we are essentially taking an image of a rock sample. We are deciding, okay, here we have some kerogen or some clay pores. We assign some probabilities for the transport of the various gases in the various pores. And then using this stochastic approach, we come up with estimates for the permeability in these rocks. And in this graph, let's see, I show you some comparison. These black crosses are our preliminary results with the kinetic Monte Carlo, and these will be the predictions if you were to use the effective medium theory. Quite a significant difference in between those two. The kinetic Monte Carlo predictions, they seem to be consistent with experimental measurements. So we are quite happy with what we've done so far in this regard, and of course we need to move further. I should mention that this is also in collaboration with my colleague Mikhail Stamatakis at UCL. Then we have some mesoscale models. This is work from Germany. The company is Geological. It's a small and medium enterprise. And here we are providing the information from the kinetic Monte Carlo in terms of permeability of the rocks. And we are looking at how the fluids permeate into a larger piece of the rock where there are some fractures already present. The recent progress in this work package, as we call them, has allowed our colleagues to look at how these fractures propagate in a small piece of the rock material. And the goal will be to use the results from this type of calculations to be embedded into the Halliburton software to predict the productivity from a shale formation. We are not there yet. Let's see if we can get there in the next year. Quite different approach. This experimental work from the University of Florence. Here we are looking at the hydraulic fracturing fluids. And the idea will be to use only green chemicals to change the properties of these hydraulic fracturing fluids. So there is a lot of work done in adding sugars and trying to understand how the viscosity of these water solutions with the sugar changes when we change the salt content. So these are some preliminary, well, actually they've published these results. They are no longer preliminary. But for example, if we look at the guargam over here, this is one of the components that were used in the first generation of hydraulic fracturing fluids. This is the viscosity as a function of shear stress. And all the curves are for the same aqueous solution that contains guargam at the same content. What changes is the type of salt that is present. So simply by changing the type of salt, you can change the viscosity of these systems by almost 2 orders of magnitude. That's quite important if you're trying to use these fluids to frack the rocks. Okay? Now what we are trying to do is to precipitate some specific components in the subsurface, like for example norm components, so that we don't bring them to the surface and we don't risk contaminating the environment when we do so. On the surface, we are using chemical engineering approaches. This is work done at the University of Alicante in Spain. To clean up the water, to find out what is the best way, the most economical way to clean up the water. We work under the assumption that in Europe, we will not be allowed to reinject water because of possible seismic consequences. So what we are trying to do is to find out what is the best technology to have no discharge of water to the surface. This is work that is proceeding at the moment. And one other thing that this group is considering is using solar power to power water cleaning technologies on the surface. Risk assessment. We have 2 people working on this subject here in the room. One is Richard and the other one is Sergey. They're sitting next to each other over there. And Sergey is looking at the possible consequences of having a well blowout. And Richard is looking at the mechanisms and possible risks that are connected with the induced seismicity. So Richard has a poster, and we'll show you something more about this, but he has been able to develop a stochastic model that has been able to reproduce experimental data from a geothermal event in Switzerland. So we are hoping that this model can be applied to a realistic scenario, and we will learn from our friends in Edinburgh about different approaches to assess the risk of induced seismicity. And finally, we have put in place a number of synergistic activities that range from trying to attract pre-university students to university degrees, MSc programs, a number of conference presentations, papers, and so on and so forth. We have external advisory boards. A number of the members of the advisory boards are sitting here. Thank you very much for taking the time to be here and help us out. We have a repository of rock, and Adrian is responsible for setting that up. Thanks again. If anybody wants to have access to those rocks, please contact us. The whole point is to make those rocks available for scientific studies. I'm quite proud that we put together this MSc in Global Management of Natural Resources. We started last year, so this picture here is the students that are about to graduate. In that picture, we just finished the Vivas in Australia about 2 or 3 weeks ago. 11 students in the first year, and we have 20 students in the second year, and they're all sitting here. So please make yourself known to our friends from industry and various universities from across Europe. With this, I think I should probably shut up. And shall I take questions, or if anybody wants to ask anything? Yeah?
I don't know a huge amount about this whole shale thing, which I suppose is why I'm here, but you said green chemicals, is that like environmental, sort of more environmentally friendly purposes? I mean, what do you mean by that?
Thanks for the question. So can you say your name now that you have the microphone for the records?
Oliveira.
All right.
Yeah.
So I should probably point out that all the presentations today are being recorded and they will be there for posterity. So behave yourself. So very nice question. So the question was, what do I mean by green chemicals when I was talking about the work from the University of Florence? So in hydraulic fracturing fluids, 98% of the components is water. Then there is some sand, and there are some chemicals. There can be surfactants, there can be viscosity modifiers, and there can be other chemicals in there. The exact composition of some of those chemicals has been posted on the web by the companies. Frac Focus is the website where you can find some information about that. What we are trying to do in Florence is to say, okay, let's try to change the properties of the solutions in terms of viscosity by only using sugars or natural products. And that's why we call them green. So the guar gum is just a natural product, and the sugars that are being used are also natural products. And we try to make alternative hydraulic fracturing fluids using those chemicals. Now, the next question that follow up from that is how far are we from making an impact on industry? And that I don't have the answer for, but you have next to you across the alley, there is Don Westacott, who can probably answer that question offline. Or if you want to answer now, it's perfectly fine.
I'm not sure I have a choice. You're pointing at me. But you asked a very, very important question here. But I believe the answer... I'm sorry. The answer goes beyond just the chemicals that the oil and gas industry is using. It's important to understand it's an end-to-end process. It's not only what we're using but what is being produced. In other words, it's not only the supply, it's the use, and it's the disposal. So it's an end-to-end product. A tremendous amount of products besides oil and gas is produced from oil and gas wells and that throughout the world. And it's really that disposal, that handling, that safe transport of those additional byproducts that is an important area of investigation and enhancement that is currently ongoing and will be ongoing for a number of years. How we minimize our total overall end-to-end footprint. But it's a great question. Thank you.
And I should also point out that Jill Scott is going to give us an overview of what Anadarko is doing in terms of reducing the environmental impact of the overall activity. Would you like to add something, Jill?
Oh, I had a question for you, actually.
Oh, you did.
I'll wait and add to the presentation. Just a brief question. You mentioned that you're looking at water treatment technologies, so you'll have zero pollutants in your discharge to surface? You're assuming you're going to keep the produced water at the surface?
So the idea there is to concentrate the salt into some solid and to have only pure water to discharge.
To discharge to surface, okay.
Now, what
When-
to do
when-
with the salt and the norm, that's a different question.
That is happening in the US. They're
Right.
using it for agriculture and we're discharging to surface. You just have to be careful when you discharge to surface and the water is too clean, you dilute your habitat.
All right.
So you might want to be careful when you say you're going to have nothing in your water, you actually don't want to have pure water going into trout habitat or fish habitat. You'll actually dilute it. So I'm sure your regulators, I think the UK is here, right? Environment. They'll tell you how to do it, but that's just a clarification for you to think about.
Thanks a lot.
Great. Thank you
Good.
very much, Alberto. That was an excellent presentation. And next, Kevin Taylor from the University of Manchester is going to tell us more about looking in detail at
Okay.
shales.
Okay, thank you. I'll just have some water to avoid a Tory conference disaster.
Resist that one.
Of course. Okay, thank you. Good morning, and thank you for Adrian and Alberto for setting us up. So we're University of Manchester. We're involved in Work Package 3, which is also involving geomechanics. But today we're going to talk about just the imaging work that we've been doing. And given it's a broad audience, we're not going to focus on the details too much, but more about the approaches we're taking, the sort of things you can do in this area, and give you a flavour of the sort of work that we're doing, but you can also obviously take and run with and you can use to help understand these systems better. As always, it's a team effort, and actually there's two others here. There's also Peter Lee at the back there, who's a Professor of Material Science in the school, and Dr. Lynn Marr, who's been working on the project, and actually Roberto, who's just started on the project as well. So any questions also addressed to them, it wouldn't work without those. I'm here representing the team. So just get the right order here. I think that's going to work. Yeah. So clearly, as has already been suggested and alluded to, we now know that, that mudstones or shales are very, very heterogeneous on multiple scales. So, from the bedding structures, which we saw some simulation of just now, some flowing through bedding structures, through fractures, down to organic matter and pores. These are all important things for understanding the rock. Now, of course, you've seen some images today already of 2D. Two-dimensional images are what the routine way of describing these rocks were, of course, up till maybe 5 years or so ago. And they're basically slices of rock which you look at under the microscope at various scales. Limitation, of course, is it doesn't give you any information about the three-dimensional structures, doesn't tell you how connected the pores are, and doesn't tell you how spatially distributed they are in the third dimension. So to jump from 2D, to get the information, obviously, of these, you need to go to three-dimensional imaging, and we can do that again at many scales. And that's the focus of the first half of this sort of very brief presentation. And then, clearly, we've already alluded to the fact we're going to fracture these shales in the subsurface. So it's clear there's a process operating on top of the natural variability, and therefore understanding how those things operate in the fourth dimension, or time, doing experiments which allow you to image three-dimensional structure change in time, i.e. 4D, is some examples in the second part of the talk, which allows you to look at these things as things behave. Now, obviously, we're not looking in the subsurface, we're looking in laboratory conditions, but we'd like to think that some of those processes we observe in the laboratory are applicable to understanding the subsurface. Oh, wrong way. So just to give you, again, those people in the room a flavour of the sort of techniques, there's been a massive expansion of the techniques available to us in the last sort of decade, really, that we use. And we can think of it in sort of a plot between scales of observation we're interested in, down to sort of resolution scale, and obviously 2D through to 4D in time. So it's a 2D to 4D plot. And I'm sure many of these things people are familiar with who have been involved in anything to do with looking at materials of any sort. So obviously small-scale imaging, you can look at things like TEM, or electron microscopy from transmission. SEM has been used for a long time, optical microscopy. So we've got many techniques, and I won't go into those details. And then, of course, as we go towards the third dimension, we have tomography, so X-ray tomography, SEM tomography, even TM tomography. So these things are available to us to try and populate the observation space we're interested in. One of the things that's also been on top of that in the last few years, and Manchester's, with Peter Lee particularly, working very carefully with Diamond, which is the synchrotron source in the UK, which gives us very high-energy X-rays, is to basically add on top of that the synchrotron source, which allows us to do a couple of things. We can get either much more high-resolution information on the two-dimensional to sort of maybe three-dimensional time scale, very long scans, or we can use the rapid availability, the rapid energy, the high energy can produce rapid imaging, which means we can actually image things in 3D, but do experiments that take minutes rather than weeks. So we can actually get the 4D. So again, we're sort of overlapping the synchrotron technology onto these sort of is the observation space. So Lynn Ma here, who's got a poster actually. So if you've got it for lunchtime, have a look at Lynn's poster. This has been published in recently, just to show that what we've been doing with multiple scales of observations and the techniques we're using for 3D. So really, if you want to get down to nanometer observations, really, which is basically where the pores are, you need to start looking at TM tomography and focused ion beam SCM techniques, which is where you basically look at an image, strip it back with a laser, an ion beam, re-image to reconstruct a three-dimensional picture. And then if you want to go and look at the next structure up, so things like the clay distributions, organics, which is a really important part of the system, through to microfractures and fractures, to the actually bigger fractures, then we can use a range of techniques from nano-CT, micro-XCT to sort of standard X-ray CT. So we can use all these techniques, and of course, they give you a limitation in their resolution. Each one's got its own resolution limitation. And one of the things which we're working on quite closely, and Lynn's been doing some work on this, is how to upscale observations to the next scale up and down again to understand how they connect together. We won't do that today. It's too much time to explain that today. So we've got basically, some of the talks I show afterwards has got basically effectively resolutions of like 1, 2, 3, 4, and 5. So resolution up here, you can see, just as a snapshot, pixelation, physical size of pixels and voxels are up in the region of sort of microns to sort of like tens of microns. And down this end, you can get resolutions of voxel size of about less than a nanometer. So you can see that each one's got its own type of resolution. So just some examples of how you can use some of these different scales. So if you look at some of the larger scale resolution, this is basically a core plug taken out of this is actually a Polish shale sample. But it's a core plug. I'll do it again. Maybe it'll actually keep going. No, it won't. Okay. You've seen it once. Remember it. Sorry about this. There we go. So we can identify fractures. This is obviously this is basically a bulk X-ray CT scan of a core plug sample, and it's very hard to see in the light, I think, but you can see there's actually mineral variability. We can extract, though, the densities, different densities of X-ray densities from those to produce an understanding of two things in his sample. It's got fractures that are mineral filled. So those are fractures which happened in the subsurface and have been refilled during burial with calcite cement. And that obviously gives you fractures which are filled. And also we have open fractures, which may be present in the subsurface, but also may be an artifact of uplifting your sample in the core, and it may be delaminating. But we can recognise those two have quite different textures, properties, and we can look at the three-dimensional geometries of those, and we can see that if we extract... Sorry, it's been a bit... Yes, next. Is it listing to... It seems to be stuck. There we go. So we can start extracting. So you can then... There we go. I think it's a very big file. I think that's probably the system. There we go. So we can start to extract the density, the thickness, and the skeletal structures of these two types of fractures. So we can start to get an indication of how these behave. And of course, fractures are very important because some people, not all people, some people feel that fractures existing in the surface, whether they're filled with calcite or not, can be reactivated upon fracking. Some people say that's not happening. So to know what the fracture distribution is, the geometry of the fractures in relation to the actual weld, for example, is an important observation to make. If we look also at next scale down, we'll be looking at organic matter distribution. How is organic matter in the rock? How distributed? What size is it? And how is it connected? Why is that important? Well, it's important because we now know, and I'm sure many of you would have read, but as I'll show in a minute, many of the pores actually in these rocks actually sit inside organic matter. They're intra-organic matter pores. So actually one of the ways in which people believe, and we believe, that gas can escape from those pores into the greater network is actually via diffusion through the kerogen and actually through into the pore system. So the better connected organic matter is, the better diffusion network you have to feed into your fractures, which then become your producing borehole. And again, we're interested in looking at we've been doing some simple experiments. This has been published this year just by Lynn again. Very simple experiments looking at samples from the same borehole but with high TOC, so 10% total organic carbon, middle TOC to low amounts of TOC. And basically, we reckon that about 6% TOC in these samples is when you get significant connectivity between organic matters. Below 6%, the organic's pretty isolated and dotted around the sample. Above 6%, you start getting organic matter connectivity, which then means you can actually start thinking about pathway through the kerogen. So this is just nice 3D movies that you can see. You can get nice images from these things as well. Which, there we go. So you can see that the organics are pretty patchy in these ones here. You start getting connectivity, and actually you start seeing the connectivity, of course, actually in the laminations, actually particularly, because the laminations tend to accumulate organic matter in one dimension. And you can then extract, if you wish to, you can use that data to extract individual organic matter types. And in these samples here for the Polish shales, there's two types of organic matter. There's basically the more sporiferous type of organic matter, and then there's also the more sort of amorphous, planar, laminated type of organic matter. So one is probably biological origin. Well, both biological, but one is probably particularly one type of spore stroke pollen, and the other is a type of probably algal amorphous algal matter. And again, you can start looking at the geometries, connectivity of these two different types in 3 dimensions. And then we can also look at the pore distribution. So these diagrams are very, very sort of hard to interpret, but what we've got here basically is pore size is put into 4 bins, the smaller pores to the larger pores. And we can recognise that not only the size variability, we can recognise that there's more than one type of pore in 3 dimensions with different sizes. So the big pores here, red, are what we call organic interface pores. They're basically pores that are quite large, and they're associated with organic matter on the outside. They could be artifactual from uplifting to laminating, but they're present in many of these samples we see in the lab conditions. And then the smaller blue ones are actually these intra-organic matter pores. They're basically below 0.1 micron in size, and they sit within the organic matter. And they're the smaller pores, but actually are the most numerous pores, but they're the smaller pores. What we can do, of course, with 3D X-ray imaging data, or FibSem data, is not just look at the size of the pores, but also information about their distribution, size, and orientation. And just for those people who are sceptical about maybe some of these things, this plot up here shows the solid curve is actually a nitrogen absorption measurement of a sample of these shales. So traditional way of measuring pore size in these rocks is using nitrogen absorption, and we get a bimodal distribution of pores in this particular system. If we combine the SEM and TEM tomography data together, we get the same bimodality, but actually in 3D from 3D images. So we're fairly confident that we're not seeing artifacts by the systems. We actually are looking at getting the 3D data that is relevant to this particular system. But of course, what you can't do with nitrogen absorption data is then say, well, what's the shape of the pores, orientation, how do the pores align to bedding planes, etc. And we can collect that data information. And again, this is in a paper we published last year by Lynn. We'll have copies. I think we've got copies here. We can send you copies if you want to. So it gives you extra level information about pores that you can't get from standard nitrogen bulk methods. Okay, so that's the first bit. I've got another 5 minutes or so just to finish off. So examples of how we might use this 3D imaging, but in a 4D manner. And one of the things that we've done a lot at Manchester and in collaboration with Diamond and Harwell is develop a range of techniques and rigs which let us do a range of experimental approaches within the beams themselves. So we have things that can actually heat the rock sample up to minus 40 to 101,500 degrees centigrade. We have mechanical pressure rigs which can obviously induce fractures. We have flow rigs where you can flow fluids through a sample. And we have, basically we can then look at these things in 4D to anywhere between 1 second to 1 minute tomographs. And then we can look at resolution down to sub-micron. You can't get to the sub-nanometer resolution in these techniques. It's very, very hard, but sub-micron is achievable. And we can also do 2 different things. We've got rigs that sit inside what we call lab source X-ray CT machines. So in Manchester and also down at Harwell, there are some X-ray machines, X-ray CTs that are lab source, so they're in a lab. And then you've got also ones that go inside the synchrotron rig. And here is this is I-13 beamline at Diamond, which is a synchrotron beam comes in here, and you can actually put a sample in here and put in front of it rigs or put it in a rig. So an example of that is something we did recently, just been published this year, which was basically an artificial maturation experiment. So we took Kimmeridge clay, which from the south coast of England is thermally immature, very high TOC construct. This is very high TOC, 50%. It's an extreme example. And we basically produced a we basically did a stepped heating in the atmosphere. We didn't confine it. It was just an open system in a furnace, just to see if we could image tomographically and in 3D where the fractures as a result of expansion or thermal evolution of gases took place. And this is just some snapshots showing these systems, gas being generated and opening up these bubble holes in the system. We can then correlate what we see to the actual thin sections and the actual SM as well. And then we took a technique called digital volume correlation, which is a three-dimensional technique which basically looks at changes in 3D between two different snapshots and works out what's moved in relation to each other. And then you can estimate, you can then calculate from that using strain models. You can calculate where the strain is forming, where the fractures start in these systems. So you basically can start producing these. You can look at these are actually where the fractures are opening up, and then you can actually work out where the strain is occurring, and you can look at these tips where the strain is taking place. And we can then correlate these to the microfabrics. And you can see we correlate these nicely to the clay organic matter interfaces that actually open up first. So we can start looking at these things on this scale, gives you an understanding of fracture propagation and formation. This is obviously a very small scale, and this is not relevant to subsurface fracking, of course, because it's a maturation, heating up, and it's not in confined conditions. But this is what Alberto alluded to very, very briefly just now, is that we've been doing some experiments also to how to get fracturing information and particularly how to get different fracture information. So how do two shells compare differently based on composition and texture using micro nano indentation, where you take your sample of shale, you basically put a pressure tip on it, you load it with a pressure tip, an indenter, put it in the I-13 beam at Diamond, and been measuring basically the deformation and the fractures as they come in. These are two-dimensional images, but we're going through the process now of producing three-dimensional images for these to produce the 3D models. This is still that work in progress. And you can see the deformation zones. But one thing that Alberto showed is that we can see different behaviour between different types of clay. So in Boland shale, which is much more homogeneous and actually quite quartz-rich and fairly brittle, we can see these fairly sheet-like fractures occurring as an indentator comes down in loading, whereas more clay-rich samples, the Kimmeridge is a good example, we see much more complicated fracture patterns forming in that limited area. Now, again, of course, it's only a small area you're indenting and fracturing, but it starts to give information about how different muds behave under different conditions, under the same conditions of fracturing, how you might produce different fracture networks. And then lastly, the last example is that we're currently doing work as part of a project looking at inducing effectively hydrofractures by pumping in fluids into pieces of shell cores, putting them basically into a confined condition, inducing hydrofracture under confined pressure conditions, putting that under the beam, and then basically imaging the injection versus time. Now, this is actually a measurement of strain from the laboratory conditions. We have beam time coming up very shortly where we'll do these experiments, but actually in the beam at Diamond. So actually imaging in 3 dimensions rather than just measuring pressure changes and where the pressure drops off as the fracture occurs. We can actually image that process in real time in 4D, provide information that you really want to understand about how the rock behaves when you fracture it. So I think that's lastly. I'm going to summarise what we have been doing. So we've been developing techniques to image in 3D and 4D at multiple scales, from nanometer to centimetre. That's the important bit. Quantifying and shale microstructures in 3D. We capture deformation and crack development in situ. That's also really important. We're carrying on. What we're doing currently is to upscale the pore properties to larger scales. Obviously, it's important to know how to upscale things. We've started using correlative 3D imaging across modes, so we have a number of techniques which we can then correlate exactly the area. Rather than taking one sample A, B, C, we take sample A, image it in one method, and we can correlate it in the next method by putting it between individual techniques. So it starts giving us much better information about one sample. And then, as I alluded just now, we're trying to capture deformation and crack development in more complex conditions, so under 3D confining pressure, etc. So I think this last thing, there's some images of the team, acknowledgements for the various people working with and the funding agencies. So a lot of this work we talked about has been Shale Environment, Shale XT. However, we've also got, obviously, funding sources from NERC, EPSERC, and the Diamond Light Source. Okay, thank you. I think it's about in time. And I'm afraid I've got to leave about 1 o'clock because I've got other duties, but Peter and Lynn will certainly be around after lunch if you want to talk to them after lunch.
That's great, thank you, Kevin. One or two quick questions.
I won't escape. I'll still be here. Yes.
With the maturation experiments, you know. Oh, sorry, Richard.
Richard, say your name, Richard.
With the maturation experiments you're currently doing, do you intend to do those in subsurface conditions as a next step?
We're currently focusing on they were really a proof of concept, actually what we could get and what times you could use, how rapid we get images. The maturation currently is, that's pretty much on the whole. What we're doing really is trying to get more hydrofracturing conditions, so using the rig to produce hydrofractures in the subsurface, using that surface conditions. So we're not, I mean, obviously we can change the temperature of those systems, and obviously that's part of it, how you change temperature, but actually the maturation experiment, which was producing gas to produce your fracturing, we're not trying to recreate that at the moment. Well, we could, but we're not trying to.
Yeah, okay. That's another area that there's a lot of research to go into.
Yeah. I mean, I think there's lots. I mean, one of the questions is how relevant is that maturation? I mean, it's a good piece of work, but how relevant is that to some of the problems we've got? And I think trying to put physical fractures in is probably more at the point in time the relevance what we're trying to achieve.
Yeah, kind of linked.
Well, they are linked. You're right. True. But I mean,
Very much linked.
yeah, interesting. We'll have to talk about that because I think the temperatures. Yeah, I mean, but that's how high you go, I guess, temperature-wise. What's the temperatures you go?
Well,
What sort of temperatures do you think?
Yeah, well, no, we know when source rock's mature, and we
Yeah.
know those windows very well.
Yeah.
I mean, you know,
Oh, yeah,
so,
absolutely,
you know,
yeah.
So you
Yeah.
need to then go into a gas window
Yeah.
or a liquid window, and you can then change those around.
Yeah.
And you can actually look at how these things mature, and then what is happening, and how does that work? Is this a kind of explosive event, like all of a sudden you get over critical pressure, and then all of these hydrocarbons, or they leak their way along through time?
Oh no, that's actually. I told you, I was probably misinterpreting. I thought you were saying, can we do these under reservoir conditions as you would frack? No, but I think if you're understanding how the systems behave through time, yeah, absolutely, that's a really interesting question.
That's going to link then back
Yeah.
into your fracture generation
Yeah.
and how we actually go after these things.
Yeah.
Because that expulsion event is critical really to the fabric of the rock.
Yeah, no, I totally agree.
Great. This is really cutting edge science from a very large scale facility, making lots of progress. And it's Ronnie Penny from Geological will talk to us.
Thank you, Adrian. Good morning to everyone. So I'm going to talk about the gas absorption properties of shale. So we are a group from Imperial College London. So the reason why we are interested in the gas absorption is, as you know by now, so the pore space in shale contains very, very small pores. They create a large surface area for gas absorption to occur. So we use gas absorption studies to probe the pore space of the shale, so to basically understand the pore space in shale, but also we use gas absorption to understand the way fluids behave within those pores. So the confinement produces a very dense gas in the pore as compared to the gas that you might find in the fracture, and this obviously needs to be taken into account when you want to estimate the amount of gas that you find in the shale, but also to understand production, because production will be, at the end of the day, limited by your ability to desorb that gas from the tight matrix. So one way to actually understand the relationship between gas absorption and production, we can use what we call a material balance approach that is used often in the industry. And the way that is applied is you produce a plot of the pressure normalized by the compressibility factor of the gas as a function of the gas that you produce. So if you're dealing with a reservoir where you don't have any absorption and production is basically based by simple decompression of gas from the pores, you will obtain a straight line. So if you have gas absorption, you will be on the right-hand side of this straight line where you start seeing the effect of the gas desorbing from the matrix. So there is a little bit more to it. So in essence, you see a number of curves here, and these actually, you get basically a different production curve depending on the type of absorption isotherm that you can see, you can observe in your shale sample. And these are actually shapes, isotherm shapes that have been reported in the literature for shale. So depending on the type of isotherm that you see, you will have a different production curve, and this actually will affect parameters like abandonment pressure, so where you will start seeing this adsorbed gas being produced at the well. So mathematically, quantifying therefore the gas in place, we require two terms. The first one is related to the gas that you find as a free gas in the pores. So you will have the density of the fluid, your porosity, but that needs to be corrected actually by the volume that is occupied now by the adsorbed fluid. And this is often neglected in the literature, but when you are at very high pressure, this density is actually large, so you can no longer neglect this term. And we're going to talk about this in a minute. And the second term is your adsorbed amount that also contributes to the gas in place. So we can recast this equation by using what we call the so-called excess sorption, which is nothing else than the difference between the absolute amount and this term proportional to the density. And basically this refers to the additional amount of gas that you find in a pore, in a nanopore, because of adsorption. So it's a very, very useful measure. So therefore, as a summary, if you want to understand gas in place, you need to understand two things. You need to understand the pore space of the shale, is your first term, but you also need to understand adsorption at very high pressure or reservoir conditions. And this is not actually a trivial task. So measuring gas adsorption in this natural system at reservoir condition is actually still a technical challenge. I'm just reporting, number of references here, but in essence, there have been attempts to do interlaboratory comparisons, and they're only partly successful, mostly because we don't have yet standards as maybe in other disciplines. Obviously, the complexity is also coming from the shale itself. It contains various minerals, clays, and organic matter, and we don't really understand yet the contribution from each of those into the adsorption properties. And actually, some contrasting observation has also been reported. In some cases, you see densification in the pores because of adsorption. In others, you actually see the opposite. And some of the complexities, actually, in understanding adsorption at high pressure is indeed that basically you move away from the traditional picture of gas adsorption that actually was established by the IUPAC many years ago, where you basically associate different adsorption isotherms to the type of materials that you are dealing with a microporous material versus a mesoporous material, and so on. When you measure adsorption at high pressure, so at supercritical condition, what you measure is an adsorption isotherm that looks like this. And this is indeed because of this definition of excess adsorption. This is what you can measure experimentally. And because it is defined as a difference between two terms, you end up having an isotherm that have a maximum and a descending part. And as you can see, they don't really fit in any of those categories. So we still lack a proper classification of this isotherm. But we can already make some interesting links, and here I indeed played with the colors from blue, black, and red between the characteristics of the materials and the type of adsorption isotherm that you measure at high pressure as compared to the type of isotherm that you see at low pressures. So this is actually an example of data collected from the literature of CO2 adsorbing at 50 degrees Celsius on a clay. In this case, it's a sodium montmorillonite. And these are various references. This is supposed to be the same sample, but as you can see, the isotherms are all over the place. And this is indeed, shows you the complexity of measuring adsorption, and this actually, obviously it's something that you need to take care of if you want to really use or introduce adsorption in your gas in place estimates. So we started basically an experimental, campaign to basically study the adsorption properties on these materials. So we have a system in our lab. It's a gravimetric system. It's a Rubotherm magnetic suspension balance. The system allows you to basically expose the sample up to very high pressure, so 350 bars, and also over a wide range of temperatures. You can go from 0 degrees up to several hundred degrees Celsius. So you can replicate the conditions that you see in the subsurface, and you can use various gases, CO2, hydrocarbons, nitrogen, and so on. So you can expose the sample to very high pressure. You can measure the weight of that sample in this very dense gas, but still measure its weight with a very high resolution. And this allows you to quantify adsorption. And so we adopted some sort of a systematic approach. So we have used samples from the Boland shale that we received from the consortium, but we also tried to basically make measurements also on some of the if we want simplified constituents. So we have been using, for instance, some pure carbons to understand how the gases interact with carbon alone, but also some source clays to indeed understand how the gas interacts with the clays alone, and try to use this information to better understand the adsorption behavior on the shale sample itself. And I will show you now some of the measurements that we performed using both CO2 and methane on a sample of the Boland shale, actually one of the same samples that was used also for the imaging experiment that we've seen in the previous talk. So these are now these excess adsorption isotherms. This is methane. We are plotting this as a function of the fluid density, but just for your understanding, so those points go up to a pressure of 250 bar. So we are covering the whole pressure range from vacuum to 250 bar. And we covered also 3 temperatures from 10 degrees up to 80 degrees. So we also go at very low temperature. That's very important to cover a wide range of temperature when you want to develop a thermodynamic model to describe adsorption in a predictive way. So you want to cover a wide range of conditions and not limit yourself only to the condition found in the reservoir. So these are the 3 isotherms that we measure. And we also measure CO2. Same conditions. The adsorption of CO2, as you can see, is significantly higher. So from this isotherm, we can now extract some estimates for adsorption capacity. So for CO2, I'm reporting it here in standard cubic meter per ton. For CO2, we measure something between 3 and 5, and slightly lower for methane, between 1 and 2. And I'm reporting here some data. Some of them we measured ourselves. Some are from the literature on some important plays in the States, so the Eagle Ford and the Barnett. And you can see, we are in the same range. The Eagle Ford we know has a larger organic content, so shows some higher adsorption. Barnett is actually similar, and indeed similar values are being reported in the literature. So some interesting observation from the adsorption data is also that there is a significant selectivity towards CO2 with respect to methane. And actually this leads to some interesting ideas of using CO2 to sweep even more gas out of the shale by enhancing the desorption of the methane once you inject the CO2. As I said, we also did measurement using some simplified systems. So here now I'm plotting. So I'm maintaining the same isotherms for the shale, the 40 and the 80 degrees, and on top of them I'm plotting isotherms measured on a mesoporous carbon, so a pure carbon material with a well-defined pore structure, so only pores of about 10 nanometers are present in that carbon. And in order to compare them to the shale data, we scale the carbon data by multiplying by a factor, and basically that factor is 5%. Interestingly, that factor is very, very close to the TOC, so the organic content of that particular shale sample that we obtain. And as you can see, by simply using that factor, the isotherm actually almost collapse on top of each other. And this actually raises a number of interesting observations. So first of all, because of the similarity, one would conclude that the organics are actually driving adsorption in this shale, because you are capturing most of it at both temperature and both gases. But also the similarity of the isotherms tell you something about the similarity in the pore structure of the two materials, because you are capturing the shape of your isotherms. We do see actually that we have some discrepancies at these high pressures and at low pressure. And these are actually indication of the presence of some very small pores that are not present in the carbon. I'm referring back to the plot that I've shown you before, and those small pores might actually be coming either from the organics itself, but or from the clays. And another important implication is also that one could maybe use these carbon materials as an analog for the adsorption properties in the organics. Again, for modeling purposes, this could be a very useful thing. So we have seen the pore space is quite complex. And we see mesopores and micropores. So we also used some standard low-pressure techniques, the nitrogen adsorption experiments, to actually understand better the pore space itself. And we've done this experiment again on the same system, so on our Boland samples, but also on the pure carbon materials, on some pure clays, and we're using here kaolinite and mormorillonite, and also on a sample from the Eagle Ford formation, which is here. So from these isotherms, you can actually extract, using some standard theories, the pore size distributions, and I'm showing this here in terms of a bar chart, And indeed, we confirm what we have seen from the high pressure experiment. So a lot of porosity in the mesopore range, so between these 2 and 50 nanometers, driving adsorption in this system. But in both shales, both the Eagleford and the Bowland and the clays, we do see also smaller pores. And this actually can be traced back to this early uptake in the adsorption isotherm that we have seen in the high pressure experiment. But the important conclusion is that there are some consistencies between this type of analysis and analysis at high pressure. So I would like to conclude with some thoughts or some preliminary results on the modeling of gas absorption. So we have seen those shale systems have complex pore structures, and also complex chemistry. We have carbons and we have clays. So if you want to understand absorption or to want to build a model, you need to move towards models that can use this information as an input parameter to your model, so that you can be better at predicting absorption in other environments. So we are following an approach based on what we call a lattice density functional theory. And making a long story short, what you can do with this model, you can select the shape and the size of your pores. In this case, we are using simply slit pores. And you can choose the thickness of those slits. And then the model basically solves the equation that describe interaction between gas molecules and also interaction between the gas molecules and the solid. In that sense, you can therefore capture the chemistry, let's say, if you want, between the gas and the components. But the good thing about the model itself is that you can then describe absorption in various pores. And as you can see in these snapshots, the profiles of the absorbed phase within pores of 1 nanometer are very different than pores of 20 nanometers. And this is actually what is causing, therefore, some of the particular shapes that we see in the absorption isotherms. So we are applying this model, and we applied it now first to a clay mineral. And our approach is basically to use one of the nitrogen isotherms and to use this isotherm to basically identify the relevant pore in your clay. And in this case, and the lines here is basically what we obtain based on the model prediction by using these pore sizes and these volumetric fractions. And these are actually in agreement with what you obtain experimentally. Once you obtain the pore sizes, we freeze them, if you want. We use those to predict the absorption at high pressure. And this is what you obtain. So these are now fresh measurements on the pure clay using CO2 from 50 up to 120 degrees Celsius, again, methane and CO2. And what we are using here is simply one parameter that describes the interaction between the CO2 and the clay, or the clay and the methane. And the rest is all pure prediction. And you can see that the model is really doing a very good job in capturing the early uptake, but also this descending part that you can typically not capture with traditional model based on Langmuir isotherm or so. Okay, so this brings me to some concluding remarks. So basically, if you want to understand the shale pore space, you need to understand gas absorption in that pore space, but the opposite is also true. You can use gas absorption to understand the pore space. So there are really important links between these two disciplines, if you want. So from the measurement that we've done so far, we see that actually shale and clay-rich system shows significant absorption capacities, and actually they retain some characteristic of a material that contains, indeed, a significant amount of mesoporosity. We do see also microporosity, so below 2 nanometers, and they might be coming from the clays. And we have also used carbon as an analog of the organic matter. For this particular sample, we obtained some good results. Obviously, we will need to extend this observation to other systems to make conclusions. But we do see significant selectivity of CO2 absorbing on the shale as compared to the methane and also on the clay. And this is obviously very interesting, as I mentioned before, for a potential production strategy. And also, these data are very useful to basically develop models that actually are more rigorous in a way, that they use information about the pore size distribution, but also the chemical heterogeneity of this system to be better at predicting absorption. This is very important when you deal with a natural material like shale, because obviously one sample taken from this borehole will be different from the other sample. Okay, so this actually was my last slide. just a few acknowledgements. Some of my students, Humera is actually here today with a poster, so you can go and talk to her, and she will have some of the absorption data there, and some collaborators on Imperial, Alberto, obviously, from University College London, for giving me the opportunity to join this project, and you for your attention. Thanks a lot.
First time I see all the results together, so quite impressive. When you were measuring the CO2 absorption on the shale samples, the Boland ones, at low temperatures, you stopped it somewhere.
Yeah.
Is it because you had too much CO2 going into those samples?
No, so at 10 degrees we stop because we reach saturation and we would liquefy CO2 into the balance, and it's something that you don't want to do. So it's simply because we reach saturation, basically.
And the other comment, have you, for the models of the pores, now not the big ones, but the small ones, have you looked at what our collaborators, Economo and Lizal, are coming up with those models for the kerogens with small pores?
Yeah, absolutely. We started actually a conversation in the meeting in Florence, and yeah, now that we have the data, I think it's the time to start, using those models on our data and see how they perform.
Excellent. Thanks.
Thank you. Thanks, Adrian.
From University of Strathclyde, who tell us about modelling gas transport.
Thank you, Andrew. Good morning, everyone. I'm Yun Haozang from Strathclyde University. I will be talking about how we understand the gas transport within the shale rock at a pore scale mainly. So because I've been working on rarefied gas dynamics, and this is a kind of application of rarefied gas dynamics. So what I'm interested in is flow models currently available to predict like permeability, fluid property of the samples. And when we have to deal with the shale rocks, then we found that the conventional kind of flow models do not work. The reasons are, first, it's shale, like a lot of speakers already pointed out, the shale pore space is very small. So we need to consider rarefaction effect. Yeah? Rarefaction effect can be measured by Lewis number, like a ratio of the gas mean free path to the pore size. And also confinement effect. That is a very, very important, which changes fluid behavior. And also for the shale production, usually often at a very high pressure. So shale gas can be in a kind of supercritical state. So this all makes conventional theory cannot apply to predict the flow property of the shale rock. And also, Ronnie just speak about the surface sorption, surface diffusion, this kind of behavior of shale samples. This is particularly important for shale gas transport. For us, like from rarefied gas dynamics point of view, for us, the challenge is how can we develop a dynamical model from surface interaction to provide the kind of boundary condition for gas kinetic sort of models. So overall, to understand the flow behavior especially at the pore scale in shale rock, we needed to consider this rarefaction effect, which needs to be modeled. And also we needed to develop a sort of dynamical boundary condition or models to consider gas absorption, gas surface diffusion, which is currently not available in gas kinetic theory framework. Also, the gas is no longer sort of normal gas, can be very dense gas. So can we resolve this? Then to predict the rock sample kind of flow property, then we need to do some kind of computational work. And computational is very expensive. So another challenge is how can we develop a high-performance computational code to deal with this. This is what we have been working on. So for some of you probably not familiar with rarefied gas dynamics, there's some background kind of information. We know that for this classical kind of experiment in a 2D channel, if you apply Navier-Stokes kind of theory to see the mass flow rate against the applied pressure, you will get this curve, the mass flow rate curve. Yeah, but actually, when you reduce the dimension of the channel becomes smaller, then you so-called, in this case, Newton number is 0.165 at the outlet. So you can see the measured mass flow rate is much higher. This is because there are two effects. One is a velocity slip at the surface, yeah, slip effect. Another is so-called Newton diffusion effect, because molecule will have more chance to collide with the wall, which form a kind of Newton-like structure, which enhance the flow rate. So in this case, the flow rate overall enhancement is 40%. Yeah, that's a straight channel. This gives us indication how mass flow rate will be affected by this kind of rarefaction effect. And also, because in this community, in pulse media flow models, people consider this so-called Klingsberg effect collection for slip flow models. But if this gives you example in a planar pressure flow at this Newton number, very small Newton number, the enhanced flow rate is 15% in this case. This 15% enhancement actually comes from, 70% is coming from slip, and 30% is come from the Newton-like structure. So when you consider like a slip correction, actually, at the same time, Newton diffusion effect may be important already. So we tend to think when you have this type of model, yeah, this, if you check a reference now literature, you will find a lot of, so this is Darcy law, then Klingsberg collection, this is a so-called Newton diffusion collection, yeah. And you will find this, we know Darcy permeability is well known, it's a flow property of the porous media, which does not depend on the flows. But then Klingsberg collection, you depend on Newton number and the so-called tangential accommodation coefficient, yeah? So TMAC, so it's very simple, clear. And then Newton diffusion collection depends on a whole row of unknown parameters, which makes these kind of models not usable. Yeah. So in the literature, when people try to use this so many tunable kind of parameters to predict flow rate, so you can always tune the parameters, get the results you want. This is a sort of example. TMAC have been used to kind of wide range of values. That's the current status of the flow model at the like a sample scale, high EV scale. But we now know we need to really forget about the Navier-Stokes kind of theory-based framework. We need to use gas kinetic kind of approach. Yeah. So in this gas kinetic community, we use like a Boltzmann equation to describe flow behavior. So if you expand on the low Newton number expansion, you can recover Navier-Stokes at low order, or first order Navier-Stokes, and you can get others. The problem for